The universe is full of wonders. Stars blaze with the fire of 1 trillion nuclear furnaces. Galaxies swirl in a cosmic dance that spans millions of years. But some things in the cosmos don't shine. They hide. They lurk in the darkness, waiting. We call them black holes. They are the ultimate monsters of the deep cosmic leviathans that swallow light itself. Nothing, not even the fastest thing in the universe, can escape their grasp once it crosses their boundary, the event horizon. This is a place of no return, a one-way trip to a destination we can only guess at. The sheer power and mystery of these objects pulls at our imagination like gravity itself. What happens inside a black hole? The laws of physics as we know them break down. At the center, we believe there's a singularity, a point of infinite density where all the matter that fell in has been crushed into an impossibly small space. It's a place where space and time become so warped, they switch roles, but we can't see it. What if the universe isn't so black and white? What if, between the familiar glow of a star and the absolute darkness of a black hole, there exists something in between, a cosmic twilight zone? This is the idea behind a gray hole. It's not a true black hole because it doesn't have an event horizon, that point of no return. But it's not a regular star either. It's an object so dense, so compact, that it comes incredibly close to becoming a black hole. It teeters on the very edge of oblivion, a place where gravity is so strong that it almost, but not quite, swallows light for good. Imagine you're trying to escape a very powerful gravitational field. On Earth you need to travel at about 11 kilometers per second, the escape velocity, to break free. For a black hole, the escape velocity at its event horizon is the speed of light. A gray hole would have an escape velocity just shy of the speed of light. Light could escape, but it would be a struggle. It would lose a tremendous amount of energy, climbing out of that deep gravitational well, appearing much dimmer than it should. One of the most intriguing candidates for a gray hole is something called a Qstar, or a quark star. To understand a Qstar, we first need to talk about what happens when a massive star dies. Its core collapses under its own immense gravity. If the core is massive enough, it crushes protons and electrons together to form neutrons. That creates a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. But what if the pressure is even greater? What if the neutrons themselves are crushed, breaking down into their own fundamental building blocks? Those building blocks are called quarks. A Qstar, then, is a hypothetical star made of a strange soup of quarks. This exotic state of matter, called quark matter, might resist collapse even more effectively than neutron matter. A Qstar would be smaller and denser than a neutron star, yet stop short of becoming a black hole. It would have a solid surface of quark matter, not an event horizon. Long before we had settled on the term gray hole, scientists were wrestling with the strange implications of Einstein's theories. In the 1970s, a fascinating and now largely forgotten idea emerged: the OTAN. The name was short for optical tunnel, an early attempt to describe an object that was gravitationally collapsed, but wasn't quite a black hole. It was born from a desire to avoid the singularity, that point of infinite density that seems so physically absurd. The OTAN was proposed as a way out, a cosmic compromise to explain extreme gravity without breaking known physics. Imagined as a supermassive object, eternally collapsing but never forming an event horizon. Instead, it sat in perpetual near-collapse. Light from its surface would be severely redshifted, effectively undetectable to us. It would look black for all intents and purposes. Stephen Hawking was a giant in the world of physics. He spent much of his life thinking about the profound weirdness of black holes. One of the biggest problems they posed is known as the black hole information paradox. According to quantum mechanics, information can never be truly destroyed. It can be scrambled, hidden, rearranged. But the fundamental details about a particle, properties. But a classical black hole, with its one-way event horizon, seems to destroy information forever. Anything that falls in is lost, and its information is wiped from existence. To solve this paradox, Hawking proposed a radical idea. He suggested that maybe black holes don't have a sharp, well-defined event horizon after all. Instead, he imagined the boundary of a black hole as a fuzzy or apparent horizon. This boundary would be a chaotic, turbulent region of quantum fluctuations. Instead of a smooth one-way door, it would be more like a stormy, unpredictable membrane. Eventually the information could leak back out. In this picture, a black hole becomes the ultimate gray hole. When we talk about how black holes or gray holes interact with the universe, we can't just think about gravity. We also have to think about radiation. Stephen Hawking famously predicted that black holes aren't completely black. Due to quantum effects near the event horizon, they should slowly emit a faint glow of particles, now known as Hawking radiation. This process causes the black hole to lose mass, and over an almost unimaginable timescale, evaporate completely. But the story is a little more complicated than that. Not all of the radiation produced near the black hole actually escapes. This is where the concept of the gray body factor comes in. You can think of it as a cosmic filter or a dimmer switch. The intense gravitational field around a black hole acts as a barrier. Some of the Hawking radiation particles that are created are immediately pulled back into the black hole before they can get away. Some particles escape. Only the particles with enough energy and the right trajectory can escape into space. The gray body factor is a number that tells us what fraction of the radiation makes it out. All of these ideas, Qstars, fuzzy apparent horizons, other gray hole models, are beautiful, elegant theories. They solve profound problems and paint a fascinating picture of the cosmos. But in science, ideas are not enough. We need evidence, we need proof. And when it comes to gray holes, proof is incredibly hard to come by. These objects are designed to be almost indistinguishable from true black holes. When two massive objects, black holes, neutron stars, spiral and merge, they send ripples through space-time. LIGO and Virgo have detected dozens of these events. The signal matched predictions for objects with event horizons. If those objects were Qstars, we might have expected an energetic echo or afterglow from colliding surfaces. The absence of that echo argues against Qstars but doesn't prove they don't exist. So if we haven't found any gray holes and all the evidence points toward classical black holes, why do we keep looking? Why do scientists spend so much time and energy chasing these theoretical shadows? The answer is simple. Because the existence or non-existence of gray holes touches upon the most fundamental questions in all of physics. It's not just about cataloging another weird object in the cosmic zoo, it's about understanding the very rules that govern reality. The quest for gray holes is a quest for the soul of the universe. At the heart of this search is the deep conflict between our two best theories of the universe: general relativity, quantum mechanics. General relativity, the theory of the very large; quantum mechanics, the theory of the very small. There must be a deeper, more fundamental theory, a theory of everything, that unites them. Gray holes are a potential solution to this conflict. They are concepts born from the marriage of gravity and quantum theory. We stand at a crossroads in our cosmic journey. For a century, the black hole has been the ultimate symbol of the unknown, a tear in the fabric of reality. But now we ask, is there a story hidden within that darkness? Could gray hole imposters populate the universe? Objects that mimic black holes but follow different rules? Are Qstars silently orbiting in the dark? Are black holes actually fuzzy quantum objects preserving information? The answers could spark a revolution in science. Imagine a future. Gravitational wave observatories so sensitive they hear two Qstars colliding, or telescopes that spot unusual radiation from a fuzzy apparent horizon. A discovery as momentous as the Higgs boson confirmation, or as the first detection of gravitational waves, it would prove new physics in extreme environments. It would open a window into quantum gravity, and set us on the path to a complete theory of everything. This is how science progresses. We start with a mystery.